Max Planck stands as one of the most significant figures in the history of modern physics, largely due to his groundbreaking work that fundamentally altered our understanding of the universe. A German theoretical physicist, Planck is best known for his discovery of the quantum nature of energy, a revelation that would eventually lead to the birth of quantum mechanics. Before his contributions, physics was dominated by classical theories, which were based on ideas that seemed capable of explaining most physical phenomena. However, these theories ran into serious limitations when they began to fail at explaining certain observations in the microscopic world. This period in history marked a profound shift, as Planck's work provided the first glimpse into a new, more accurate framework for understanding the nature of matter and energy. The scientific community in Planck's time was firmly rooted in classical physics, a domain that was largely defined by figures like Isaac Newton and James Clerk Maxwell. Newton's laws of motion and gravitation, along with Maxwell's equations governing electromagnetism, had created a comprehensive framework that seemed to explain most macroscopic phenomena in the universe. This classical view was comfortable, predictable, and all-encompassing for a long period. But in the late 19th century, physicists began to encounter problems that classical physics could not resolve. One such issue was the problem of black body radiation, which was pivotal in shaping the path that Planck would take in his revolutionary discovery. Black body radiation refers to the electromagnetic radiation emitted by an idealized object known as a blackbody, which absorbs all radiation that falls on it and emits radiation based solely on its temperature. Classical theories, particularly the Rayleigh-Jeans law, were unable to explain why the observed radiation from a black body diverged from theoretical predictions at higher frequencies. Classical physics predicted that as the frequency of radiation increased, the energy emitted would grow infinitely, leading to what was known as the ultraviolet catastrophe. This was a glaring discrepancy between theory and experimental observation, and it suggested that the laws governing radiation at small scales were not fully understood. Planck's breakthrough came when he proposed a new theory to solve this problem. Rather than treating energy as a continuous variable, as classical physics had done, Planck suggested that energy could only be emitted or absorbed in discrete amounts, or quanta. This idea was radical because it challenged the very foundations of classical physics, which was based on the assumption that energy could vary smoothly in any amount. Planck's insight was that energy was not emitted in a continuous flow but in packets of energy, each proportional to the frequency of the radiation. Planck's work was initially inspired by his efforts to find a formula that could match experimental data on black body radiation. In 1900, after months of meticulous work, Planck derived an equation that described the distribution of energy in the radiation emitted by a black body. This equation, known as Planck's law, fit the experimental data perfectly. It explained why the amount of radiation emitted by a black body increased with temperature and why it peaked at a certain frequency. The formula also eliminated the ultraviolet catastrophe by introducing the idea of quantization, where energy could only exist in discrete chunks, with each chunk corresponding to a frequency of radiation. Although Planck's solution to the black body radiation problem was a remarkable achievement, the true implications of his work were not immediately apparent. Planck himself was somewhat hesitant to embrace the full consequences of his theory. He initially viewed his concept of energy quanta as a mathematical trick to explain the data, not as a fundamental feature of nature. However, the implications of his work began to unfold in the years that followed, as other scientists began to recognize the profound implications of Planck's discovery. One of the first to build upon Planck's work was Albert Einstein, who, in 1905, extended the idea of energy quantization to explain the photoelectric effect. In the photoelectric effect, light striking a metal surface can cause the emission of electrons, but only light of certain frequencies, or energies, can produce this effect. Einstein proposed that light, which had traditionally been treated as a wave, could also behave as discrete particles, or photons, each carrying a quantum of energy. This insight was a direct consequence of Planck's work and helped establish the concept of wave-particle duality, a cornerstone of quantum mechanics. Niels Bohr also took inspiration from Planck's theory when he developed his model of the atom. Bohr's atomic model, introduced in 1913, was based on the idea that electrons in an atom could only occupy specific orbits with quantized energies. This concept of quantized energy levels in atoms was revolutionary, as it provided a way to explain the discrete spectral lines observed in the light emitted by atoms. Bohr's model, which was heavily influenced by Planck's work, provided a new framework for understanding atomic structure and laid the groundwork for the development of quantum mechanics. Planck's contributions didn't end with his work on black-body radiation. His introduction of the concept of energy quanta and his constant, which became known as Planck's constant, would go on to have far-reaching effects across the field of physics. The introduction of Planck's constant, denoted as h, was a pivotal moment in the history of science. It provided a fundamental unit for the measurement of energy and allowed physicists to describe the behavior of particles and waves at the quantum level. Planck's constant, which has a value of approximately 6.62, 6 times 10, negative 34 joule-seconds, is now recognized as one of the most important constants in physics, playing a central role in quantum mechanics, quantum field theory, and the understanding of atomic and subatomic systems. Although Planck did not fully embrace the radical implications of his work, his discoveries opened the door to an entirely new way of thinking about the universe. The theory of quantization led to the development of quantum mechanics, a field of physics that challenges our intuitive understanding of reality. In the quantum world, particles can exist in multiple states simultaneously, they can be entangled over vast distances, and their behavior is governed by probabilities rather than certainties. These ideas were incomprehensible to the classical physicists of Planck's time, and even Planck himself initially struggled to accept the full implications of his theory. However, over time, the scientific community came to embrace the new quantum paradigm, and Planck's work was recognized as the cornerstone of this transformative shift in physics. Max Planck's discovery was more than just a theoretical breakthrough. It was the beginning of a revolution in how we understand the fundamental nature of the universe. By introducing the concept of quantized energy, Planck not only solved a critical problem in black-body radiation, but also provided the foundation for the entire field of quantum mechanics. The consequences of his work are still unfolding today, as quantum theory continues to shape our understanding of everything, from the behavior of subatomic particles to the development of new technologies like quantum computing. Planck's theory fundamentally shook the foundations of classical physics, introducing a new paradigm that would forever change the landscape of scientific thought. His work on the quantization of energy opened the door to a deeper understanding of the universe and allowed scientists to develop a more accurate and comprehensive view of reality. Although Planck did not live to see the full impact of his discoveries, his contributions to physics are immeasurable. Today, Max Planck is recognized as one of the founding fathers of quantum theory, and his work continues to influence scientific research and technological innovation across a wide range of fields. Planck's legacy is not just one of theoretical discovery, but also of inspiring future generations of physicists to challenge conventional wisdom and explore the mysteries of the universe in new and uncharted ways. The advent of quantum mechanics and the profound questions it raised about the nature of reality would not have been possible without the insight and courage of Max Planck, whose vision transformed our understanding of the physical world. The quantum revolution that Planck began continues to unfold, with its implications reaching from the smallest particles in nature to the largest cosmic structures, fundamentally altering how we think about the universe. Max Planck's revolutionary theory, which introduced the concept of quantization, became the cornerstone for what would later evolve into quantum mechanics. Planck's work shattered classical physics and reshaped our understanding of the universe. His most significant contribution was not just the explanation of blackbody radiation, but also his establishment of a new way of thinking about energy itself. The implications of his ideas extended far beyond the confines of theoretical physics and laid the groundwork for the development of technologies that would emerge in the 20th century, including quantum computing, lasers, and advancements in materials science. The idea that energy is quantized, meaning it exists in discrete packets, was a dramatic departure from the continuous nature of energy that classical physics had long embraced. Planck's insight was born out of his efforts to resolve the issue of blackbody radiation, a puzzle that had troubled scientists for decades. Classical physics, particularly the Rayleigh-Jeans law, had predicted that at higher frequencies, the intensity of radiation emitted by a black body would increase infinitely, which didn't align with experimental observations. Planck approached this problem by introducing a radical idea: energy could not be emitted or absorbed continuously, but instead occurred in discrete amounts, or quanta. This idea was encapsulated in what would later be known as Planck's constant, denoted by **h***, a fundamental constant of nature that governs the scale of the quantum effects. With the introduction of Planck's constant, the concept of energy levels became quantized, meaning that the energy of a system could only take specific values. This discrete nature of energy was revolutionary because it contradicted the prevailing notion that energy was continuous. While Planck himself initially viewed his hypothesis as a mathematical convenience to explain the data, the work laid the foundation for future developments in quantum theory. Planck's law, which he derived in 1900, described how the intensity of radiation emitted by a black body varied with temperature and frequency. This law was an accurate mathematical formula that explained how energy is distributed in radiation and resolved the ultraviolet catastrophe. The law stated that the energy emitted at each frequency was proportional to both the frequency and a factor based on the temperature of the object. The crucial element in the law was the introduction of the quantum of action, a fixed quantity of energy determined by Planck's constant. His equation could match experimental data that classical physics failed to explain. Despite the elegance and accuracy of his law, Planck himself struggled to embrace the full implications of his discovery. He initially believed that his quantization was merely a temporary fix to a particular problem rather than a fundamental property of nature. However, over time, his work laid the foundations for quantum mechanics, as other physicists began to build on his ideas. Albert Einstein's work on the photoelectric effect in 1905, for example, applied Planck's quantization of energy to light itself, leading to the revolutionary idea that light, previously understood solely as a wave, could also be thought of as particles, or photons. Einstein's interpretation of the photoelectric effect was a direct consequence of Planck's work, as it explained why light of certain frequencies could eject electrons from a metal surface. Niels Bohr also embraced Planck's quantization in his atomic model. Bohr's model, which described the behavior of electrons in atoms, posited that electrons could only occupy specific, quantized orbits around the nucleus. This idea, which would eventually lead to the concept of quantized energy levels in atoms, was grounded in Planck's theories. The Bohr model successfully explained the discrete spectral lines observed in the emission and absorption spectra of atoms, a key piece of evidence that the classical understanding of atomic structure was incomplete. The discovery of quantization by Planck was not just a shift in understanding energy, but also a shift in how we thought about the very nature of reality itself. Planck's theory was the first stepping stone in what would eventually lead to the birth of quantum mechanics, a field that would defy classical intuition and introduced concepts like wave-particle duality, uncertainty, and superposition. The behavior of particles at the atomic and subatomic levels was revealed to be governed by probabilities rather than deterministic laws, a radical departure from the certainty of classical physics. In the years following Planck's initial work, the scientific community began to realize that the old models of physics were no longer sufficient to explain the behavior of the microscopic world. Planck's introduction of quantized energy levels catalyzed the development of a new field of physics that would eventually become quantum mechanics. The next major steps were taken by other scientists, such as Werner Heisenberg, who formulated the uncertainty principle, and Erwin Schrödinger, who developed the wave equation to describe the wave-like behavior of particles. These developments, built on Planck's foundation, would forever change the landscape of physics. One of the lasting legacies of Planck's theory is its connection to modern technology. While Planck's work was initially theoretical, it laid the groundwork for technologies that harness the principles of quantum mechanics. The development of the transistor, for instance, relies on quantum principles like energy quantization and electron behavior in semiconductors. Lasers, which are based on the principles of quantum mechanics, have become essential tools in fields ranging from telecommunications to medical diagnostics. Quantum computing, which aims to exploit the strange behavior of particles at the quantum level, is another area where Planck's discoveries play a pivotal role. Planck's constant, which represents the smallest possible unit of action in quantum mechanics, is a fundamental building block of our understanding of the universe. It is used to define the size of quantum effects and plays a crucial role in various quantum mechanical equations. The importance of Planck's constant extends far beyond theoretical physics and influences a wide array of fields, including chemistry, materials, science, and even cosmology. Planck's work helped us understand the discrete nature of energy, which has profound implications for everything from the behavior of elementary particles to the properties of the universe at its most fundamental level. Planck's influence extended beyond his scientific contributions. His careful, methodical approach to problem solving, his willingness to challenge established norms, and his perseverance in the face of resistance became an inspiration for generations of scientists. Although Planck himself did not live to see the full impact of his work, the theories he helped create continued to drive the exploration of the quantum world. His legacy is felt not only in the halls of academia, but also in the technologies that shape our everyday lives. Today, Planck is regarded as one of the fathers of quantum physics, a field that continues to revolutionize our understanding of the universe. The impact of Planck's theory is not just confined to physics, but resonates through the scientific community and society at large. By introducing the concept of quantization, Planck pushed the boundaries of human knowledge, opening up new avenues of research that would lead to profound discoveries in physics, chemistry, and even the philosophy of science. His work set the stage for the great advances of the 20th century, shaping the way we approach the study of matter, energy, and the very fabric of the universe itself. In conclusion, Max Planck's theory, which introduced the concept of quantized energy, fundamentally changed our understanding of the universe. His work solved long-standing problems in black-body radiation and laid the foundation for quantum mechanics. While he may have initially viewed his discovery as a mathematical tool, his theory would go on to revolutionize science. Today, Planck's constant remains a fundamental constant in physics, and his legacy continues to shape our exploration of the atomic and subatomic realms, influencing everything from technology to our very conception of reality. Through his groundbreaking work, Planck not only changed the course of physics but also opened the door to a new era in science, one that continues to unfold. Max Planck's discovery of energy quantization and the formulation of Planck's law marked a pivotal moment in the history of physics. It challenged the classical understanding of energy and laid the foundation for the quantum revolution that would forever alter our perception of the universe. One of the most significant outcomes of Planck's work was his introduction of the Planck constant, denoted by H**, a fundamental physical constant that governs the scale of quantum effects. This discovery was not just a mathematical innovation, but a key that unlocked a deeper understanding of how energy behaves at the smallest scales, influencing everything from the behavior of subatomic particles to the development of technologies that shape our modern world. Before Planck's breakthrough, classical physics, governed by Newtonian mechanics and Maxwell's equations of electromagnetism, had been remarkably successful in explaining macroscopic phenomena. These classical theories held that energy was continuous and could vary smoothly in any amount. However, the emergence of new experimental challenges, like the problem of black body radiation, showed that classical physics could not explain certain observations, particularly at the atomic and subatomic levels. The classical laws of physics predicted that the energy emitted by a black body would increase without bound as the frequency of the radiation increased, a prediction that did not match experimental data. This discrepancy, known as the ultraviolet catastrophe, spurred scientists to search for a new theory that could explain the observed radiation patterns. In 1900, Max Planck took on the task of solving this problem. Drawing upon his understanding of thermodynamics and electromagnetism, Planck proposed a revolutionary idea. Energy, instead of being continuous, could be emitted or absorbed only in discrete packets, or quanta. This was a radical departure from the continuous nature of energy that classical physics had assumed. Planck introduced the concept of the quantum of action, now known as Planck's constant, which is the smallest possible unit of energy that can be transferred or emitted. By introducing this concept, Planck not only solved the problem of blackbody radiation, but also provided the first glimpse of a new paradigm in physics. Planck's equation for blackbody radiation, known as Planck's law, described how the intensity of radiation emitted by a black body varies with temperature and frequency. His formula correctly predicted the amount of radiation emitted at various frequencies, resolving the ultraviolet catastrophe that had stumped classical physics. The key element of Planck's law was the introduction of the quantum of energy, which could only take discrete values based on the frequency of the radiation. This idea of quantization fundamentally altered the way scientists thought about energy. It meant that energy was not a smooth, continuous flow, but a series of discrete steps, each proportional to the frequency of the radiation. This insight was the first step in what would become the field of quantum mechanics. The Planck constant, denoted by H**, became a fundamental unit of measurement in physics. It was introduced into Planck's law as a proportionality constant between the energy of radiation and its frequency. Planck's constant has a value of approximately 6.626 x 10, -34 joule-seconds, and it plays a critical role in quantum mechanics. It governs the relationship between energy and frequency in the quantum world, where particles and waves are no longer treated as separate entities, but as complementary aspects of the same reality. The Planck constant not only helped to resolve the blackbody radiation problem, but also set the stage for the development of quantum theory, a new framework for understanding the microscopic world. The consequences of Planck's discovery went far beyond blackbody radiation. Planck's idea that energy was quantized would become a central tenet of quantum mechanics, influencing the work of later scientists like Albert Einstein, Niels Bohr, and Werner Heisenberg. Albert Einstein, for instance, extended Planck's idea of energy quantization to light, explaining the photoelectric effect. In this phenomenon, light of a certain frequency can cause the emission of electrons from a metal surface. Classical wave theory could not explain why only light above a certain frequency could produce this effect. Einstein proposed that light was not just a wave, but also consisted of discrete packets of energy, which he called photons. This concept, based on Planck's work, helped establish the wave-particle duality of light and laid the groundwork for the development of quantum mechanics. Niels Bohr, too, was heavily influenced by Planck's theory when he developed his model of the atom. In 1913, Bohr proposed that electrons in an atom could only occupy certain discrete orbits around the nucleus, with each orbit corresponding to a specific energy level. These energy levels were quantized, meaning that the electrons could not occupy arbitrary orbits, but only specific, quantized ones. This idea was directly inspired by Planck's work, and it provided an explanation for the discrete spectral lines observed in the light emitted by atoms. Bohr's model marked a significant step toward the modern understanding of atomic structure and was a key development in the field of quantum mechanics. The birth of quantum mechanics, with its strange and counterintuitive ideas, can be traced directly back to Max Planck's discovery of energy quantization. Planck's introduction of the quantum of energy challenged the classical understanding of the world, where energy was assumed to be continuous and infinitely divisible. Instead, Planck's work showed that energy was fundamentally discrete, and this insight would form the basis for the entire field of quantum mechanics, which describes the behavior of matter and energy at the smallest scales. Quantum mechanics introduced ideas like wave-particle duality, uncertainty, and superposition, which defy classical intuition but have been experimentally verified in countless experiments. The implications of Planck's discovery extend far beyond the realm of theoretical physics. Quantum mechanics, born out of Planck's ideas, has had a profound impact on technology, leading to innovations in fields as diverse as computing, telecommunications, and medicine. The development of the transistor, for example, which is the basis for modern electronics, relies on quantum mechanical principles like energy quantization and electron behavior in semiconductors. Lasers, which have become essential tools in fields ranging from telecommunications to medical diagnostics, also rely on quantum principles. More recently, the field of quantum computing has emerged, with the potential to revolutionize computation by harnessing the power of quantum mechanics to solve problems that are intractable for classical computers. Planck's constant, which remains a fundamental constant of nature, is used to describe the scale of quantum effects in a wide variety of systems, from elementary particles to macroscopic systems. It is a key element in the equations that govern the behavior of particles and waves in the quantum world. The value of Planck's constant is one of the most precisely measured quantities in physics, and it plays a central role in our understanding of the microscopic universe. Its significance extends beyond theoretical physics and has practical applications in the development of quantum technologies. Planck's legacy is immense, and his work continues to shape the future of physics and technology. His theory of quantized energy changed the course of science, challenging the classical worldview and opening the door to a new era of physics. Although Planck did not live to see the full impact of his work, his ideas have had a lasting influence on the scientific community, inspiring generations of physicists to explore the strange and fascinating world of quantum mechanics. Today, Planck is regarded as one of the founding fathers of quantum theory, and his work remains central to our understanding of the fundamental nature of the universe. Planck's contributions were not limited to his scientific discoveries alone. He was also a tireless advocate for scientific integrity and intellectual honesty. Throughout his career, Planck emphasized the importance of approaching scientific problems with rigor and humility, acknowledging the limitations of current knowledge while remaining open to new ideas. His commitment to the pursuit of truth and his willingness to challenge established ideas set an example for future generations of scientists. Max Planck's work transcended the boundaries of physics and has had a profound impact on the way we understand the world, influencing not only the scientific community but also society as a whole. Max Planck's discovery of quantization fundamentally changed the course of science, shifting the paradigm from the continuous nature of classical physics to the discrete, probabilistic nature of quantum mechanics. His work laid the foundation for one of the most successful and transformative theories in physics, and its consequences continue to shape the way we view the universe. Planck's constant remains one of the most important constants in physics, and his legacy is deeply embedded in the development of modern science and technology. Through his groundbreaking work, Max Planck changed the way we understand the universe at its most fundamental level, and his influence will continue to resonate for generations to come. Max Planck's formulation of energy quantization was a watershed moment in the development of modern physics. It laid the groundwork for what would become quantum mechanics and radically altered our understanding of how the universe operates at the microscopic scale. The concept of energy quantization, first introduced by Planck in 1900, revealed that energy could not be treated as a continuous flow, but instead existed in discrete units, or quanta. This insight not only solved an existing problem in the theory of blackbody radiation, but also opened up entirely new avenues of research that would fundamentally challenge classical physics and lead to the development of quantum mechanics. At the heart of Planck's work was his investigation into blackbody radiation. A blackbody, in physical terms, is an idealized object that absorbs all radiation incident upon it and re-emits that energy. The study of how black bodies radiate energy at different temperatures was a problem that had plagued physicists for decades. Classical physics, particularly the Rayleigh-Jeans law, predicted that as the frequency of radiation increased, the amount of radiation emitted would continue to grow without bound, leading to what became known as the ultraviolet catastrophe. Experimental data, however, showed that this prediction was incorrect, particularly at higher frequencies, where radiation actually dropped off, rather than increasing infinitely. This discrepancy between theoretical predictions and experimental data was a major obstacle in the field of physics at the time. Planck took on the challenge and proposed a novel approach that would reconcile the theoretical and experimental differences. Instead of assuming that energy could take on any arbitrary value, as classical physics had done, Planck suggested that energy could only be emitted or absorbed in specific discrete amounts. These amounts, or quanta, were proportional to the frequency of the radiation being emitted. This proposal led to the introduction of the Planck constant, denoted as **H**, which became a fundamental quantity in the new quantum theory. Planck's law, which described how the energy emitted by a black body varied with temperature and frequency, was a breakthrough in the scientific community. The law accurately predicted the radiation spectrum of black bodies and resolved the ultraviolet catastrophe. The most important aspect of Planck's work was his proposal that energy was not continuous, but quantized. He introduced a constant **H** that linked energy to frequency in a way that made energy a discrete entity rather than a continuous variable. The equation he developed showed that the energy of a quantum of radiation was proportional to its frequency, with the Planck constant being the constant of proportionality. This was the first formal introduction of the idea that energy could only exist in fixed, discrete packets, laying the groundwork for the entire field of quantum mechanics. Planck's law was not just a theoretical solution to a specific problem, but it opened up a new way of thinking about energy. The idea that energy could only exist in discrete amounts was revolutionary. Classical physics had always assumed that energy could be divided infinitely into smaller and smaller units. This assumption had worked well for macroscopic phenomena, but failed when applied to the behavior of atoms and light. Planck's insight was a critical departure from this classical view and introduced a fundamental shift in how physicists understood the nature of energy. The concept of quantization would go on to shape the entire field of quantum mechanics, influencing later developments by physicists like Albert Einstein, Niels Bohr, and Werner Heisenberg. Planck's introduction of the concept of quantized energy paved the way for Einstein's explanation of the photoelectric effect. In 1905, Einstein applied Planck's ideas to the behavior of light and proposed that light, which had previously been thought of as a wave, could also be thought of as consisting of discrete particles called photons. Einstein's work on the photoelectric effect demonstrated that light could only eject electrons from a metal surface if its frequency was above a certain threshold. This discovery was a direct consequence of Planck's quantization hypothesis and led to the development of the particle-wave duality concept, which would become a cornerstone of quantum mechanics. Niels Bohr's model of the atom also grew directly from Planck's ideas. In 1913, Bohr introduced his atomic model, which proposed that electrons in atoms could only occupy specific, quantized orbits around the nucleus. This quantization of electron orbits was a direct application of Planck's concept of quantized energy. Bohr's model explained why atoms emitted light at specific frequencies, producing the discrete spectral lines observed in atomic spectra. The model was an immediate success and was built upon the foundation that Planck's work had established. While Planck initially viewed his theory of energy quantization as a mathematical tool to solve a specific problem, its implications would turn out to be far-reaching. Planck himself was hesitant to accept the full implications of his work, viewing it as a temporary expedient rather than a fundamental change in the understanding of nature. He did not fully appreciate that his discovery would eventually lead to the development of quantum mechanics, a revolutionary new framework for understanding the microscopic world. Despite his initial reservations, the concept of quantized energy quickly gained traction in the scientific community, and it became the foundation upon which future physicists would build the field of quantum theory. The development of quantum mechanics, with its strange and counterintuitive ideas, was the next logical step after Planck's discovery. Quantum mechanics would introduce concepts like wave-particle duality, the uncertainty principle, and superposition, all of which defied the classical understanding of the world. The work of Planck, Einstein, Bohr, Heisenberg, and Schrödinger collectively transformed physics, leading to the emergence of a new way of thinking about matter and energy. Quantum mechanics, although difficult to grasp at first, has since been validated by numerous experiments and has become one of the most successful theories in the history of science. Quantum mechanics, born from Planck's insights, has had a profound impact on technology. The development of the transistor, a key component of modern electronics, relies on quantum principles such as energy quantization and the behavior of electrons in semiconductors. Lasers, which are used in everything from telecommunications to medical applications, also rely on quantum effects. More recently, quantum computing has emerged as a new frontier in information technology, promising to revolutionize the way we process and store information by harnessing the strange properties of quantum systems. One of the most enduring legacies of Planck's work is the introduction of Planck's constant, **H**, which has become a fundamental constant in physics. The Planck constant defines the scale of quantum effects and governs the relationship between energy and frequency in quantum systems. Its value, approximately 6.626 x 10, -34 joule-seconds, plays a crucial role in many quantum mechanical equations and experiments. The Planck constant is central to our understanding of the microscopic world and is used in a variety of fields, from atomic physics to cosmology. Max Planck's discovery of quantized energy was not just a theoretical breakthrough, it marked the beginning of a new era in physics. The ideas that he introduced challenged classical physics and laid the foundation for the development of quantum mechanics, which has since become one of the most successful and transformative theories in science. Planck's work continues to shape our understanding of the universe at the smallest scales, influencing not only the theoretical study of physics, but also the development of technologies that impact our daily lives. Planck's contributions to science are immeasurable, and his legacy continues to inspire future generations of physicists, engineers, and scientists as they push the boundaries of knowledge and explore the quantum world that he helped to unlock. Max Planck's work, particularly his introduction of quantization and the establishment of Planck's constant, served as the catalyst for a scientific revolution that would unfold over the next century. His theories marked a departure from classical physics, which had dominated the understanding of the universe for centuries, and ushered in the era of quantum mechanics. The implications of Planck's discoveries were far-reaching, not only in reshaping our understanding of energy and matter at the microscopic level, but also in laying the groundwork for the technological advancements of the 20th and 21st centuries. His work influenced generations of physicists and continues to shape the way we think about the fundamental principles of the universe. Before Planck's time, the classical physics paradigm, established by Newtonian mechanics and Maxwell's equations, had been remarkably successful in explaining large-scale phenomena. These classical theories were based on the assumption that energy and matter behaved in a smooth, continuous manner, and for many years this view proved sufficient for understanding the observable world. However, as science advanced and technology improved, certain experimental observations began to challenge the classical understanding of physics. One such challenge was black-body radiation, a problem that had plagued physicists for many years and would lead to Planck's revolutionary insight. A black body is an idealized object that absorbs all radiation that falls on it, and then re-emits this energy at different wavelengths depending on its temperature. The problem, known as the black body radiation problem, was that classical physics predicted an unrealistic increase in the intensity of radiation emitted by a black body at high frequencies. This prediction led to what was called the ultraviolet catastrophe, where classical laws suggested that energy would increase infinitely at shorter wavelengths, which was not observed in reality. The discrepancy between theoretical predictions and actual observations spurred a re-examination of the foundational assumptions of classical physics. Planck's solution to this issue was groundbreaking. In his work, he proposed that energy is not continuous, as had been traditionally assumed, but instead comes in discrete amounts, or quanta. In doing so, he introduced the concept of the quantum of action, a fundamental idea that would form the backbone of quantum theory. The energy emitted by a body, Planck suggested, could only take on certain specific values, and this energy was directly proportional to the frequency of radiation. This insight provided the missing piece that would explain the observed radiation spectrum and eliminate the ultraviolet catastrophe. In his 1900 paper, Planck derived an equation that accurately described the distribution of energy in black body radiation. This equation, known as Planck's law, resolved the inconsistencies in classical physics and described the energy distribution of radiation at various temperatures and frequencies. At the core of his equation was the Planck constant, denoted asterisk, H asterisk, a fundamental physical constant that governs the scale of quantum effects. The Planck constant, with a value of approximately 6.626 x 10, negative 34 joule seconds, was the key to understanding the discrete nature of energy. This constant became the fundamental unit of measurement for energy at the quantum level and set the stage for a new era in physics. Although Planck initially viewed his discovery as a mathematical solution to a particular problem in black body radiation, the implications of his work soon became clear. The concept of quantized energy challenged the classical view, which treated energy as a continuous variable. Planck's discovery hinted at the existence of a world beyond the reach of classical physics, a world where energy did not flow smoothly, but instead existed in discrete packets, governed by a fundamental constant. This insight was the first step in the development of quantum mechanics, a new framework for understanding the behavior of matter and energy at the atomic and subatomic levels. Planck's work set the stage for the later development of quantum mechanics by inspiring other physicists to explore the implications of quantization. One of the earliest and most significant extensions of Planck's theory came from Albert Einstein in 1905, when he applied the concept of energy quanta to explain the photoelectric effect. The photoelectric effect describes the phenomenon where light striking a metal surface causes the emission of electrons. Classical wave theory could not explain why light of certain frequencies caused the ejection of electrons, while light of lower frequencies did not, despite the fact that both types of light carried the same intensity. Einstein proposed that light, which had traditionally been thought of as a wave, could also be thought of as consisting of discrete packets of energy, or photons. This idea was directly influenced by Planck's work on energy quantization, and it was a key moment in the development of quantum theory. Einstein's work on the photoelectric effect earned him the Nobel Prize in Physics in 1921 and provided further validation of Planck's revolutionary ideas. Another important development that arose from Planck's work was Niels Bohr's model of the atom, which he introduced in 1913. Bohr applied Planck's concept of quantization to the structure of the atom, proposing that electrons in an atom could only occupy certain discrete energy levels. This was a direct application of Planck's ideas, and Bohr's model helped explain the discrete spectral lines observed when atoms emitted or absorbed light. Bohr's atomic model was one of the key milestones in the development of quantum mechanics, and laid the groundwork for the later work of physicists like Werner Heisenberg, who would go on to develop the uncertainty principle, and Erwin Schrödinger, who formulated the wave equation to describe the behavior of quantum particles. The consequences of Planck's work extended beyond theoretical physics. His introduction of quantized energy led to a number of technological advances that have shaped the modern world. Perhaps the most well-known technology that emerged from quantum theory is the transistor, which relies on quantum principles like energy quantization and electron behavior in semiconductors. The transistor, invented in the 1940 seconds, is the fundamental building block of modern electronics, and it has revolutionized the fields of computing, telecommunications, and information technology. Without Planck's work on energy quantization, it is unlikely that the development of semiconductor technology and, by extension, the digital age, would have been possible. Another groundbreaking technology that emerged from quantum mechanics is the laser, which was developed in the 1960 seconds. Lasers rely on the principles of quantum mechanics, including energy quantization and the stimulated emission of radiation, both of which trace their origins back to Planck's work. Lasers have found applications in countless fields, from telecommunications and medical diagnostics to manufacturing and entertainment. The development of quantum technologies, like the transistor and the laser, demonstrates the lasting impact of Planck's theories on the real world. In addition to these technological advances, Planck's work also had a profound influence on the philosophy of science. The advent of quantum mechanics raised fundamental questions about the nature of reality and our ability to know and understand the world at its most fundamental level. Planck himself was reluctant to fully embrace the philosophical implications of his work, but the development of quantum mechanics would lead to new debates about the nature of observation, measurement, and the role of the observer in the physical world. These philosophical questions, which were explored by thinkers like Niels Bohr and Werner Heisenberg, continue to resonate in discussions about the nature of quantum reality. Planck's legacy is not only scientific but also cultural. His introduction of energy quantization and the Planck constant opened up an entirely new way of thinking about the universe. The strange, counterintuitive world of quantum mechanics, which emerged from Planck's work, continues to challenge our understanding of reality and the limits of human knowledge. The principles of quantum mechanics have shaped everything from the way we study atomic structures to the way we think about the behavior of particles at the most fundamental level. In conclusion, Max Planck's discovery of energy quantization and the development of Planck's constant represent a monumental shift in the history of physics. His work not only solved a long-standing problem in blackbody radiation, but also paved the way for the development of quantum mechanics, a theory that would revolutionize our understanding of matter, energy, and the universe itself. Planck's legacy extends far beyond his scientific contributions, influencing the development of quantum technologies and shaping the philosophical debates surrounding the nature of reality. Planck's ideas continue to inspire physicists and thinkers to this day, and his work stands as one of the most profound milestones in the history of science. Max Planck's discovery of energy quantization and his formulation of the Planck constant marked the dawn of a new era in physics, reshaping our understanding of the universe at its most fundamental level. Planck's theory, initially conceived to solve a specific problem in blackbody radiation, evolved into the cornerstone of quantum mechanics, a revolutionary framework that would forever change how we perceive matter and energy. This new perspective on the microscopic world broke with centuries of classical physics, introducing ideas that seemed almost incomprehensible to scientists of the time. However, it laid the groundwork for many of the most profound advances in science and technology over the last century. The problem that Max Planck set out to solve was the blackbody radiation problem, which had confounded physicists for many years. A blackbody is an idealized object that absorbs all radiation incident upon it and re-emits this energy as electromagnetic radiation. Classical physics, based on the laws of thermodynamics and electromagnetism, predicted that as the frequency of radiation increased, the amount of emitted radiation would continue to grow without bound, leading to the so-called ultraviolet catastrophe. This prediction contradicted experimental observations where the intensity of radiation actually decreased at higher frequencies. The failure of classical physics to explain the behavior of black bodies at high frequencies exposed a gap in our understanding of energy and radiation. In 1900, Max Planck proposed a radical solution to this problem. He introduced the idea that energy is not emitted or absorbed continuously, as classical theory suggested, but rather in discrete packets, which he called quanta. The key insight here was that the energy of these quanta was directly proportional to the frequency of the radiation. This relationship was mathematically expressed by the equation E equals hfc dot f, where E is the energy of the quantum, HA is Planck's constant, and F is the frequency of the radiation. This was a revolutionary idea because it challenged the long-standing assumption that energy could vary smoothly. Instead, Planck's hypothesis suggested that energy came in fixed, discrete units, fundamentally changing how physicists viewed the behavior of energy. The introduction of the Planck constant, h, was the pivotal moment in this shift. Planck's constant, which has a value of approximately 6.626 times 10 negative 34 joule-seconds, became one of the most important constants in physics. It effectively set the scale for the quantization of energy and provided a way to understand the behavior of energy at the atomic and subatomic levels. The quantization of energy also provided a mathematical framework for understanding how black bodies radiate energy at different temperatures and frequencies, thus resolving the ultraviolet catastrophe. The Planck constant became a fundamental unit for measuring the smallest possible units of energy, and its introduction would go on to influence every major development in quantum physics. While Planck himself did not immediately recognize the full implications of his discovery, his work laid the foundation for the future development of quantum mechanics. His insight into the quantization of energy would inspire other physicists, most notably Albert Einstein, to explore the consequences of this new view of the world. In 1905, Einstein used Planck's idea of quantization to explain the photoelectric effect. The photoelectric effect describes how light striking a metal surface can cause the emission of electrons, but only light of a certain frequency has enough energy to eject these electrons. Einstein proposed that light, which had traditionally been viewed as a wave, could also be thought of as being made up of discrete particles, which he called photons. This extension of Planck's ideas helped confirm that energy was not just quantized in blackbody radiation, but that light itself was also quantized, providing another critical step in the development of quantum mechanics. Niels Bohr's work on the structure of the atom also drew heavily on Planck's ideas. In 1913, Bohr proposed a model of the atom in which electrons could only occupy specific, quantized orbits around the nucleus. These orbits corresponded to specific energy levels, and electrons could transition between these levels by absorbing or emitting a quantum of energy. This model, which explained the discrete spectral lines observed in atomic spectra, was directly inspired by Planck's idea of quantized energy levels. Bohr's atomic model provided a new way of understanding atomic structure and helped solidify the idea that energy in the atomic world is quantized rather than continuous. The true significance of Planck's work became increasingly clear as other physicists began to develop the field of quantum mechanics. The theory of quantized energy fundamentally altered the way scientists approached the study of the microscopic world. Quantum mechanics introduced new concepts that defied classical intuition, such as wave-particle duality, uncertainty, and superposition. These concepts suggested that at the atomic and subatomic scales, particles could behave both like waves and particles, and their properties could only be described in terms of probabilities rather than certainties. Quantum mechanics provided a more accurate and comprehensive description of the behavior of matter and energy at these scales, and it has since become one of the most successful theories in the history of science. The consequences of Planck's work extended beyond the realm of theoretical physics. His introduction of energy quantization was the catalyst for a host of technological advancements that would shape the modern world. One of the most significant of these was the development of the transistor, which is the foundation of modern electronics. The behavior of semiconductors, which are central to transistor operation, can only be understood in terms of quantum mechanics. The principles of energy quantization and electron behavior in semiconductors were directly influenced by Planck's work, and the transistor revolutionized computing, telecommunications, and nearly every other area of modern technology. Another groundbreaking technology that arose from quantum theory was the laser. Lasers rely on the concept of stimulated emission, in which an electron in a higher energy state drops to a lower energy state, emitting a photon in the process. This phenomenon can only be understood in terms of quantized energy levels, and the development of lasers in the 1960 seconds provided a practical application of quantum mechanics. Lasers have since found widespread use in fields ranging from telecommunications to medicine, manufacturing, and entertainment. Beyond technology, Planck's work also had a profound influence on the philosophy of science. The advent of quantum mechanics raised deep questions about the nature of reality and the limits of human knowledge. Quantum mechanics suggested that at the most fundamental level, the universe behaves in ways that are fundamentally indeterminate, and that the observer plays a role in shaping the outcomes of experiments. These ideas have led to ongoing debates about the nature of reality, measurement, and observation, and have influenced philosophers of science, such as Heisenberg and Bohr, in their exploration of the implications of quantum mechanics for our understanding of the universe. Max Planck's legacy is not just scientific, but also cultural. His introduction of energy quantization and the Planck constant opened up an entirely new way of thinking about the universe. The strange and counterintuitive world of quantum mechanics, which emerged from his work, continues to challenge our understanding of reality and the limits of human knowledge. The principles of quantum mechanics have shaped everything from the way we study atomic structures to the way we think about the behavior of particles at the most fundamental level. Planck's work has left an indelible mark on both the scientific community and society at large, and his contributions continue to influence the development of science and technology today. In conclusion, Max Planck's discovery of quantized energy and his formulation of the Planck constant represent a monumental shift in our understanding of the physical world. His work solved a long-standing problem in black-body radiation and laid the foundation for the development of quantum mechanics. Planck's ideas have had far-reaching consequences, not just in physics but in technology, philosophy, and society. Through his groundbreaking work, Planck changed the course of science and our understanding of the universe, and his legacy continues to shape the future of scientific inquiry and technological innovation. His insights into the nature of energy and matter remain a cornerstone of modern physics, and his influence will continue to be felt for generations to come. Max Planck's work on energy quantization and his introduction of Planck's constant was the breakthrough that paved the way for quantum mechanics, fundamentally changing the landscape of modern physics. One of the most significant aspects of his discovery was the resolution of the black-body radiation problem, a challenge that had stumped scientists for decades. Classical physics, specifically the Rayleigh-Jeans law, predicted that the intensity of radiation emitted by a blackbody would increase without bound at higher frequencies, an observation that contradicted experimental data. Planck's solution to this issue was to propose that energy could not be emitted continuously, as previously assumed, but rather in discrete units or quanta. This concept of energy quantization was revolutionary, marking the first significant break from classical physics and laying the groundwork for the quantum theory that would follow. Planck's law, which described how energy was distributed across different frequencies of radiation, provided an accurate formula for the observed radiation emitted by a black body. The key to Planck's law was his introduction of a fundamental constant, known as Planck's constant, denoted as asterisk, asterisk, h asterisk, asterisk, which described the relationship between energy and frequency. This constant, with a value of approximately 6.626 times 10 negative 34 joule seconds, became a fundamental quantity in quantum mechanics and set the scale for quantum effects in the microscopic world. Planck's law not only resolved the ultraviolet catastrophe, but also established energy quantization as a fundamental concept in physics, forever changing our understanding of energy and matter. The second major contribution of Planck's work was his role in the development of the quantum theory that followed. While Planck himself did not fully embrace the implications of his discovery, his introduction of energy quantization served as a foundation for subsequent developments in quantum mechanics. His ideas were built upon by physicists like Albert Einstein, who extended the concept of energy quantization to explain the photoelectric effect. Einstein's work, which showed that light behaves both as a wave and as discrete particles called photons, directly resulted from Planck's pioneering work. Similarly, Niels Bohr used Planck's ideas when developing his model of the atom, proposing that electrons in an atom could only occupy specific, quantized energy levels. These developments were key steps in the emergence of quantum mechanics, which would later redefine the laws of physics at the atomic and subatomic levels. The third important aspect of Planck's work was the lasting impact of his theory on modern technology. Although Planck's initial focus was on theoretical problems in black-body radiation, the principles of quantum mechanics that his work inspired have become fundamental to a variety of technological advancements. The transistor, for example, relies on quantum mechanics to control the flow of electricity in semiconductors, enabling the development of modern electronics and computers. Similarly, lasers, which operate based on the principles of stimulated emission and quantized energy levels, have become indispensable in fields ranging from telecommunications to medicine. Planck's work helped lay the foundation for these technologies, which have transformed every aspect of modern life. Lastly, Planck's work had a profound philosophical impact on the scientific community. The introduction of energy quantization marked a shift from the deterministic worldview of classical physics to the probabilistic and often paradoxical realm of quantum mechanics. Quantum mechanics, as developed from Planck's insights, suggested that at the atomic level, the universe does not behave according to the smooth, predictable rules of classical physics. Instead, it operates on principles of uncertainty, where particles can exist in multiple states at once, and their properties are governed by probabilities rather than certainties. This challenge to classical determinism raised profound questions about the nature of reality, the role of the observer, and the limits of human knowledge. These questions continue to shape the philosophical and theoretical debates surrounding quantum mechanics to this day. In summary, Max Planck's theory of energy quantization and his introduction of Planck's constant were groundbreaking contributions that had far-reaching implications for both theoretical physics and technology. His work resolved key problems in blackbody radiation, set the stage for the development of quantum mechanics, and inspired technologies that have transformed the modern world. Moreover, Planck's discoveries challenged the foundational assumptions of classical physics and gave rise to new philosophical questions about the nature of reality itself. Today, Planck's legacy endures, as his ideas continue to shape scientific research and technological innovation across a wide range of fields. Max Planck's groundbreaking discovery of energy quantization fundamentally reshaped the landscape of modern physics and paved the way for the development of quantum mechanics. One of the most important aspects of Planck's work was his resolution of the blackbody radiation problem, a long-standing issue that had eluded classical physics. Classical theory, especially the Rayleigh-Jeans law, predicted that the energy emitted by a black body would increase without bound at high frequencies, which led to what was known as the ultraviolet catastrophe. The experimental data, however, showed that this was not the case, and the intensity of radiation actually dropped at higher frequencies. This discrepancy prompted Planck to explore a new way of thinking about energy, which ultimately led to his proposal that energy could only be emitted or absorbed in discrete units or quanta. Planck's insight into the quantization of energy was revolutionary. By introducing the concept of energy being released in discrete packets, he was able to create an equation that accurately described the observed distribution of energy emitted by a black body. This equation, known as Planck's law, replaced the classical laws and fit experimental data perfectly. The key to this equation was the Planck constant, which is now regarded as one of the most fundamental constants in physics. Planck's constant, denoted as H**, has a value of approximately 6.62, 6 times 10, -34, joule seconds. This constant is essential for understanding the scale of quantum effects and plays a pivotal role in quantum mechanics, establishing a bridge between the macroscopic world of classical physics and the microscopic world governed by quantum laws. The second key aspect of Planck's discovery was its long-lasting influence on the development of quantum mechanics. While Planck himself did not initially fully appreciate the far-reaching implications of his work, the concept of quantized energy was the starting point for subsequent developments in quantum theory. Albert Einstein, in 1905, extended Planck's quantization idea to explain the photoelectric effect, showing that light behaves both as a wave and as discrete particles called photons. This was a major leap in understanding the dual nature of light, and Einstein's work earned him the Nobel Prize in Physics. Niels Bohr's atomic model, which proposed that electrons orbit the nucleus in discrete energy levels, was also built upon Planck's idea of energy quantization, explaining the discrete spectral lines of atoms. These developments were critical in the emergence of quantum mechanics as a fully formed theory. The third key area of Planck's impact was the technological revolution that his theories helped to inspire. Although Planck's work was primarily theoretical, the implications of his theories have been realized in numerous technologies that have transformed the modern world. Quantum mechanics, born from Planck's introduction of quantized energy, is the foundation of many modern technologies. One of the most significant inventions made possible by quantum mechanics is the transistor, which is the building block of all modern electronics. Transistors are crucial in devices like computers, smartphones, and countless other electronic systems. Additionally, lasers, which operate on quantum mechanical principles such as stimulated emission and energy quantization, are essential in fields ranging from telecommunications to medical treatment. These innovations, rooted in Planck's ideas, have revolutionized industries and reshaped everyday life. Another significant aspect of Planck's work was its philosophical implications. Planck's introduction of quantized energy led to the emergence of quantum mechanics, which challenged the deterministic worldview of classical physics. Classical physics was built on the idea that the behavior of particles and objects could be predicted with precision given enough information. However, quantum mechanics, arising from Planck's discovery, suggests that at the atomic and subatomic levels, the behavior of particles is inherently probabilistic. The principle of uncertainty, first formulated by Werner Heisenberg, further challenged classical notions of predictability by stating that certain properties of particles, such as their position and momentum, cannot both be precisely measured at the same time. This uncertainty has profound philosophical implications, particularly in our understanding of reality and the role of the observer in shaping the outcomes of experiments. Lastly, Planck's legacy continues to shape the way we approach science today. His work on energy quantization laid the foundation for a new approach to physics, where understanding the microscopic world required a departure from classical thinking. Quantum mechanics, which arose from Planck's discovery, remains one of the most successful and influential theories in the history of science. It not only provides the most accurate descriptions of atomic and subatomic systems, but also continues to drive innovations in technology and research. Furthermore, Planck's work has prompted ongoing philosophical discussions about the nature of reality, measurement, and observation, challenging our conventional understanding of the universe. His contributions to science have set the stage for future discoveries and will continue to guide physicists in their quest to understand the deepest mysteries of the universe. Max Planck's contributions to the field of physics were revolutionary, and his introduction of energy quantization marked the beginning of quantum theory, which would forever change the understanding of the universe. One of the most significant aspects of his work was his solution to the black-body radiation problem. Prior to Planck's work, classical physics, specifically the Rayleigh-Jeans law, predicted that the intensity of radiation emitted by a black body would increase indefinitely at higher frequencies, which was inconsistent with experimental observations. Instead of energy increasing indefinitely, the intensity dropped at high frequencies. This discrepancy led to the ultraviolet catastrophe, a major flaw in classical physics. Planck's introduction of energy quanta, where energy is emitted or absorbed in discrete packets, solved this problem and resolved the inconsistencies in classical theory. Planck's law, which he derived in 1900, explained how energy is distributed across different frequencies of radiation emitted by a black body. By introducing the idea that energy is quantized and comes in discrete units, Planck showed that the energy emitted by a black body at a given frequency is proportional to the frequency itself. The introduction of Planck's constant **** h***, which is approximately 6.626 times 10^-34 joule seconds, provided a scale for quantum effects and became one of the most significant constants in modern physics. This constant linked the frequency of radiation with the energy associated with that radiation, effectively solving the long-standing problem of black body radiation. The second pivotal aspect of Planck's discovery was the lasting impact it had on the development of quantum mechanics. While Planck's work initially addressed a specific problem in thermal radiation, it became the foundational idea upon which quantum mechanics was built. One of the first to expand on Planck's quantization concept was Albert Einstein, who, in 1905, applied the idea to explain the photoelectric effect. Einstein demonstrated that light behaves as discrete packets of energy, or photons, rather than just as a continuous wave. This work, directly inspired by Planck's theory, showed that energy was quantized not just in radiation, but also in light itself. This discovery was crucial in establishing the dual nature of light and advancing the field of quantum mechanics. Planck's work also significantly influenced Niels Bohr's atomic model, which he proposed in 1913. Bohr suggested that electrons in an atom could only occupy specific quantized orbits around the nucleus, with each orbit corresponding to a fixed energy level. These quantized orbits explained the discrete spectral lines observed when atoms absorbed or emitted light. Bohr's model was one of the first to incorporate Planck's idea of energy quantization, and it provided an explanation for phenomena that classical physics could not. This marked a key milestone in the development of atomic theory and quantum mechanics. A fourth significant contribution of Planck's theory was its far-reaching impact on the development of technology. Although Planck's work was theoretical in nature, it provided the foundational understanding of quantum mechanics that would later drive major technological advances. Quantum mechanics, based on Planck's concept of energy quantization, is the cornerstone of modern electronics. The invention of the transistor, which relies on quantum principles, revolutionized the electronics industry and paved the way for computers, smartphones, and virtually all modern electronics. Similarly, the laser, which operates on principles of quantum mechanics, has had a profound impact on fields ranging from telecommunications to medicine. The direct influence of Planck's work can be seen in the technologies that shape our everyday lives. The philosophical implications of Planck's work were also profound. Before Planck, physics was governed by deterministic principles, where the behavior of objects could be predicted precisely, given the right initial conditions. Planck's discovery of energy quantization challenged this view, suggesting that at the atomic and subatomic levels, nature behaves in a fundamentally probabilistic way. This realization was further developed by physicists like Werner Heisenberg and Erwin Schrödinger, whose work on the uncertainty principle and wave mechanics highlighted the inherent uncertainties in measuring the properties of particles. Planck's work introduced the idea that, at the quantum level, particles do not have definite positions and momenta, but instead exist in a superposition of states. This shift from determinism to probability had deep philosophical implications for how we think about the nature of reality. Lastly, Planck's legacy continues to shape the field of physics today. His introduction of quantized energy marked the beginning of a new era in physics, and his work laid the foundation for the development of quantum mechanics. Quantum theory has since become one of the most successful and widely accepted theories in modern science, explaining a vast array of phenomena from the behavior of atoms and molecules to the properties of materials. Planck's constant remains a central figure in quantum mechanics, appearing in many fundamental equations and experiments. Furthermore, his discovery set the stage for ongoing research in quantum technologies, including quantum computing, which promises to revolutionize the way we process and store information. Planck's work continues to inspire physicists and engineers, guiding the exploration of the quantum world and shaping the future of science and technology. In summary, Max Planck's discovery of energy quantization was a turning point in the history of physics. His work not only solved the blackbody radiation problem, but also introduced the concept of quantized energy, which would become the foundation of quantum mechanics. Planck's constant provided a fundamental scale for quantum effects and set the stage for later developments in the field. His discoveries also influenced the development of atomic theory, technology, and philosophical discussions about the nature of reality. Today, Planck's legacy endures as one of the most influential figures in the history of science, and his work continues to guide research in quantum physics and technology. Max Planck's introduction of the concept of energy quantization in 1900 marked a revolutionary moment in the history of physics. Before Planck's breakthrough, classical physics assumed that energy was continuous, flowing smoothly between states. However, certain phenomena, particularly black-body radiation, could not be explained within this framework. Classical theories predicted that, as the frequency of radiation increased, its energy would grow infinitely, an outcome known as the ultraviolet catastrophe. Experimental observations, however, revealed that radiation intensity dropped at high frequencies, presenting a significant contradiction to classical predictions. Planck's solution to this problem was to propose that energy is not emitted continuously, but in discrete amounts, or quanta. This simple yet profound idea laid the groundwork for quantum mechanics. The core of Planck's solution was the introduction of Planck's constant, denoted **H**, which served as the proportionality factor between the energy of a quantum and its frequency. Planck's equation explained how energy was distributed across different frequencies of radiation emitted by a black body. The equation successfully matched experimental data, resolving the ultraviolet catastrophe that had puzzled physicists for years. Planck's law of blackbody radiation not only provided an accurate description of radiation patterns, but also introduced a new, quantized view of energy, one that fundamentally departed from the classical understanding of the continuous nature of energy. The second key development resulting from Planck's work was the birth of quantum mechanics. Although Planck himself viewed energy quantization as a mathematical tool to solve a specific problem, the implications of his theory were far-reaching. His work on energy quantization inspired other physicists to explore the consequences of this new perspective. Albert Einstein, in 1905, extended Planck's ideas to the photoelectric effect, showing that light could be understood as being composed of discrete packets of energy called photons. This discovery was pivotal in establishing the dual nature of light, which behaved both as a wave and a particle. Einstein's work built directly on Planck's theory and helped cement the idea of quantization as a core tenet of quantum mechanics. Niels Bohr's atomic model, introduced in 1913, was another significant outcome of Planck's work. Bohr applied the idea of quantization to the structure of the atom, proposing that electrons orbit the nucleus in specific quantized energy levels. These quantized orbits explained the discrete spectral lines emitted by atoms, a phenomenon that classical physics could not account for. Bohr's model was a major leap forward in understanding atomic structure, and it further demonstrated the power and applicability of Planck's quantum ideas in explaining the behavior of atoms and their interactions with light. A fourth major consequence of Planck's theory was the development of new technologies. The principles of quantum mechanics that Planck's work inspired would later form the foundation for groundbreaking inventions like the transistor, which became the cornerstone of modern electronics. Quantum mechanics also enabled the development of lasers, which have transformed industries from telecommunications to medicine. Today, the practical applications of Planck's ideas are seen in a vast array of technologies that have revolutionized how we live and work. Without Planck's introduction of quantized energy, these innovations would have been impossible. The fifth aspect of Planck's legacy lies in the philosophical implications of his work. The quantization of energy suggested a shift from the deterministic view of the universe upheld by classical physics to the probabilistic nature of quantum mechanics. In classical physics, objects were expected to behave in predictable, deterministic ways. However, quantum mechanics, born from Planck's insights, introduced the idea that at the atomic and subatomic level, nature behaves probabilistically. The Heisenberg uncertainty principle, which states that certain properties of particles, like their position and momentum, cannot both be precisely measured simultaneously, is a direct result of the shift in thinking initiated by Planck's work. These developments raised profound questions about the nature of reality and the role of the observer in determining the outcome of measurements. Sixth, Planck's work helped pave the way for a new understanding of the fundamental constants of nature. The Planck constant, He, is one of the most significant constants in modern physics. It represents the scale of quantum effects and governs the relationship between energy and frequency in quantum systems. Planck's constant plays a crucial role in many areas of physics, including quantum field theory, particle physics, and the study of atomic systems. The significance of this constant cannot be overstated. It remains a fundamental quantity in the equations that describe the behavior of matter and energy on the smallest scales. Lastly, Planck's influence on modern physics cannot be overstated. His work laid the foundation for the development of quantum mechanics, which has since become one of the most successful and transformative theories in science. Quantum mechanics continues to shape our understanding of the microscopic world and has driven innovations in fields ranging from material science to computer technology. Planck's legacy is evident in the ongoing development of quantum technologies, including quantum computing, which promises to revolutionize information processing and computation. As our understanding of quantum physics continues to evolve, the foundational contributions of Max Planck remain central to the progress of science. In conclusion, Max Planck's discovery of energy quantization and his introduction of the Planck constant represented a paradigm shift in physics. His work resolved long-standing problems in black-body radiation and laid the foundation for the development of quantum mechanics. The implications of his discoveries have been far-reaching, influencing the work of future physicists, leading to technological innovations, and shaping the philosophical landscape of science. Today, Planck's legacy lives on in the continued advancement of quantum physics and the technologies that have become an integral part of modern life. His work remains a cornerstone of our understanding of the universe,